In the last video, we came up with the phenomenon of discontinuity to describe when it is that it's okay to evaluate a limit just by plugging in the x value. What we came up with is, first of all, we defined continuity. A function is continuous at an x value a if the limit at that x value is equal to the value of the function at that x value. And we figured out what that looks like on a graph. A function is continuous at an x value, a, if there's no break in the graph at a. So to check our understanding of this idea, let's look at a couple examples of functions and decide where are they continuous. So here's a function. F of x is the absolute value of x over x. And let me ask for this function, where is f continuous? All right. Well, to get a handle on where this is continuous, I guess we should figure out what the graph of this looks like, because it's not totally obvious what the graph of this looks like. It's kind of a strange combination of an absolute value and the regular variable x. Not really clear what this looks like. One way to work with absolute value is to always write it as a multi-part function. So let's rewrite this function. It is, let's see, in the denominator we always just have x, but the numerator, the absolute value, what the absolute value is depends on whether x is positive or negative. So if x is greater than or equal to 0, the absolute value doesn't do anything, because if x is positive, the absolute value is just the same thing. So that would be just x. And I guess since we have an x in the denominator, we actually can't have x be 0. Okay? The other possibility is if x is negative, well, the denominator is still just x, but the numerator, if the thing inside an absolute value is negative, the absolute value puts an extra minus sign on it. So that means this numerator is minus x. If x itself is negative, then minus x is actually positive because there's two minus signs here. The minus sign that I have written down and the one that's hiding inside of x because x is negative. Well, for both of these possibilities for this function f, we can simplify them. For the first one, we just get 1, and for the second one, we get minus 1. So this lets us sketch the graph of this function. For negative x values, this function is minus 1, so like this. And for positive x values, this function is plus 1, like that. Okay, now that we know what the graph of this looks like, it's pretty straightforward to figure out where this is continuous. We just have to ask ourselves, where are there breaks in the graph? And the only break in the graph is at x equals 0. So at x equals 0. So this function is continuous for every x value. So it's continuous everywhere except x equals 0. If we want to, we could describe what kind of discontinuity this is. Because the graph jumps from one value to another, this is a jump discontinuity. Okay, let's look at another example. For our next example, let's call this function g of x. And we're going to look at x minus 2 over x squared minus 4. Now before we start working with this, let's just make a note of what the domain of this function is. Because the denominator factors as x minus 2 times x plus 2, we can't let x be 2 or minus 2 because that would mean we're dividing by 0. So the domain is x values besides 2 and minus 2. Okay. Well, to decide what discontinuities we have, Again, it's easiest to find a graph for this, but this rational function is a little bit complicated. Coming up with a graph might be tricky, but of course, if you noticed when I factored, the denominator has a factor that matches the factor in the numerator. So we can simplify this function by canceling those factors. We get 1 over x plus 2, but these factors only cancel when x isn't 2. So this equation that I wrote down, this is true for every x value except 2. All right. So to graph this function, to graph g, what we're going to do is graph 1 over x plus 2, but then remember that when x is 2, that point actually isn't in the domain of our function. So let's graph 1 over x plus 2. 1 over x plus 2 looks just like 1 over x, except since we've replaced x with x plus 2, that shifts the graph left 2 units. All right, so 1 over x looks like this dotted green graph. And when we shift that to the left 2 units, the vertical asymptote shifts over to minus 2. And that means it's going to look something like this. All right. But remember, x equals 2 isn't actually in the domain of this function. So let's mark where x equals 2 is. It looks like it's about here. So this point that looks like it's on the graph, it actually isn't. So we need to punch a hole in the graph at that point. Okay, so here's our graph of g. And now that we have a graph of g, we can identify where the discontinuities are. So discontinuities. And we're just asking ourselves, where does the graph jump around? And it looks like there are 2 places. At x equals minus 2, because there's this vertical asymptote here, the graph sort of jumps from minus infinity up to plus infinity. So there's a discontinuity at minus 2. And over at 2, there's a gap in the graph. It doesn't really jump up or down, there's just a hole. And that means x equals 2 is a discontinuity. Well, let's describe what types of discontinuities these are. So at x equals minus 2, since the graph is going down to minus infinity on one side and up to minus infinity on the other side, that means this continuity at minus 2 is an infinite discontinuity. And at x equals 2, since there's a hole in the graph, we could fill in this hole to fix the discontinuity. And that means that this is a removable discontinuity. All right, so we have 2 discontinuities, one at minus 2 and one at 2. And the function is continuous everywhere except those 2 x values. All right, so if you can get some idea of what a graph looks like, it's pretty straightforward just by looking at the graph to see where the discontinuities are. But actually, it's kind of a hassle to have to draw the graph. It would be nice if there were some easier way to know where a function is continuous. So let's ask ourselves, in general, what kind of functions are continuous? So just try to imagine what graphs can you think of that don't have any jumps in them. And there are actually large categories of graphs that are always continuous. So one kind of graph you might think of is a polynomial. Right, something like x to the 4th minus 3x plus 4. If you've graphed polynomials, you know that they never have any breaks in the graph. Polynomials are continuous everywhere. All right. What about rational functions? A rational function is a ratio of polynomials, kind of like this example that we looked at earlier, x minus 2 over x squared minus 4. Well, this wasn't continuous everywhere, but that's because there were some holes in the domain. Except for the holes in the domain, there weren't any discontinuities. And it turns out that's true for all rational functions. So rational functions are continuous on their entire domain. They aren't continuous where they have holes in the domain, but that's not a big surprise because, right, continuity is, the definition of continuity is that the limit at an x value is equal to f of a, but if f of a doesn't even exist because a isn't in the domain of f, then that equation can't be true. All right, so what other kinds of graphs? What about trig functions? Like, say, sine or tangent, all of these guys. Well, if you imagine the graph of trig functions, so for example, sine, that's the one that looks like this, and tangent, that's the one that looks like this. They're always nice unbroken curves, except where there's a hole in the domain, right? For example, tangent has these spots where it jumps from plus infinity to minus infinity, but that happens where there's a hole in the domain of tangent. As long as you ignore the holes in the domain, none of these graphs jump around. So trig functions are also continuous on their entire domain. All right, let's look at some other examples. What about exponentials or logarithms? Well, exponentials, the graph of an exponential looks something like this. That doesn't have any discontinuities. And the graph of a logarithm, because it's the inverse of an exponential, it looks something like this. And that doesn't have any discontinuities either. Well, as long as you stick to the domain of the natural logarithm, right? To the left of 0 over here, there is no graph, so we can't talk about the graph being continuous because there's just no graph over here. So natural log is continuous where it's defined. Well, that means, again, it's continuous on its entire domain. What we're finding here is that most formulas that we write down, they're continuous on their entire domain. So actually, almost all functions are continuous almost everywhere. And that makes a lot of limits very easy to calculate. Let's look at a quick example. Let's find the limit as x goes to, I don't know, how about pi over 3 of sine squared x over x plus 4. Okay, well, sine is continuous. Right? Raising something to a power doesn't change continuity. Dividing by x plus 4, well, x plus 4 isn't 0 at pi over 3. All of these operations sort of behave nicely with continuity. And so this function is continuous where it is defined. And since it's defined at pi over 3, we can just plug in pi over 3. Right? Continuity means you can evaluate a limit just by plugging in the x value. This function is continuous, so we can just plug in the x value. So we get sine squared of pi over 3, over pi over 3 plus 4. And then we could do all the arithmetic to evaluate this, to simplify this expression. So sine of pi over 3 is root 3 over 2, and that squared is 3 over 4 over pi over 3 plus 4. And then I guess if you wanted to, you could rearrange this fraction. You get 3 over 4 times pi over 3 plus 4. We could multiply the numerator and denominator by 3 to get rid of this pi over 3 part. So that would give us, let's see, multiplying by 3, that would give us 9 over 4 times pi plus 12. Okay, so for a function that's continuous, evaluating a limit really is just a matter of plugging in the x value. What we'll see is that most of the limits we're interested in, the function isn't continuous where we want to evaluate the limit. And so we will have to do some trickery to turn the function into something that is continuous, because then we can just plug in the x value.